Tonight I wanted to talk to you about different types of forces and solve some different types of force problems. But before I do that, I want to do some housekeeping and just kind of talk to you guys about what is due this week, because I know we've got a lot due to the hurricane last week. So almost everyone has a due date tomorrow, 9/20. Okay, so that's the 18-week kids, the 16-week kids, and the 14-week kids. All of y'all have due dates tomorrow, and it will be the assignments from the that were due the 13th and the 20th. You've got an extension on those 13th assignments because of the hurricane. And then let's talk about some other things. So tomorrow, on the 20th, the 16-week kids will need to take their Newton's Laws test. Okay, that's what the schedule says. And this is important because, one, tests are worth 40% of your grade, but also because this test is actually due on the 20th. So it's on your schedule for the 20th and is due on the 20th. I know sometimes, a test might not, a test might be scheduled for Friday, and so you may not take it till Tuesday or Wednesday when it's due on Wednesday. But this one actually is scheduled for Wednesday and is due on Wednesday. So if you don't turn it in tomorrow, you'll lose, you won't get full credit on that test. So that's really important to do. The 22nd, which is Friday, the 14-week students will need to take their 2D motion test. And I have some reviews I posted for this on our page under user links. So make sure that you check out those reviews before you take the test. I think it would be helpful and help you do well on the test. On the 22nd, which again is Friday, the 12-week students are going to take their math and physics test. So that's that very first unit, remember. You guys are going to want to take that math and physics test. And it's important, 12-week kids, that you guys don't get behind, because your class goes faster than everyone else's class, because you're doing what the 18-week students are doing. It's taking them 18 weeks to do. You're going to be doing that same amount of material in 12 weeks, so you're going to have a lot more due each week. So it's going to be important that you stay on top of that. And then next Wednesday, everyone has a due date. And this is literally everyone. The 18-week kids, the 16-week kids, the 14-week kids, and the 12-week kids. Everyone's got a due date next week. Okay. So that's the really important things for this week, especially that due date tomorrow, because there's a lot of assignments, because you do have the assignments from the 13th and the 20th due tomorrow. So make sure you guys are working on those. Now let's talk about weight and different types of forces. So what I did is I broke the forces up into sections, and then on this title slide or whatever, I went ahead and wrote the formula for you. So if you're following along and you've got a formula sheet that you've been working on all semester, you'll want to write these formulas on your formula sheet so you've got them for your quizzes and tests. I do have a formula sheet under user links for you, but just in case you're building your own, you'll want to write these formulas. If you haven't started building a formula sheet, you really want to do that, because you don't want to be looking up the formulas in the middle of the test or the quiz or anything like that. You want to have those formulas ready to go so you're ready to take that test. And so it'll also save you some time on some of those tests that have lots of long problems, that you need all that time. having those formulas ready to go will help you with those tests. So your weight is basically your force of gravity. Your weight is not equal to your mass. So your mass is intrinsic to you. You have a specific mass, and your weight has to do with gravity. So for example, I have a certain weight on Earth, which is a lot right now because I'm pregnant. But if I were to go to the moon has less gravity, and so I weighed less, and I actually would weigh less because the gravity on the moon is less than the gravity on Earth. Now, the gravity on Earth, we call that little g. My students said that sounded like a rapper, little g. But we also know this is like free fall acceleration. We call it gravity. And that's that little g of 9.8 meters per second squared, which we were using in the projectile problems. We're going to continue using that. That's why I mentioned if you memorize this number, which you should, you're going to get your mileage out of it. You're going to use it a lot this semester. So it's to your benefit to just go ahead and memorize it because you're going to need it. And G always points towards the center of the Earth. So if you remember with our free body diagrams, our weight always went to the center of the Earth when we drew those last week. And again, this is our formula. Fg equals your mass times gravity, and that's your force due to gravity. So you'll see that all of them, like in the course website, they let me see if I can find a good color. In the course website, you might see the formula looking like this. I like to keep it force due to gravity or force due to friction or whatever. That way I know that I'm always know I'm dealing with a force because I've got a F here. So that's just kind of something that I do. So here's a problem. Let's try and solve it. So this is a problem. Let's see. The yellow is pretty less slide, but let's try something else just for the heck of it. Ooh, that's too pink. Okay. So what is your weight on Earth if your mass is 65 kilograms? Okay, so this is our mass. They want the weight. That's Fg, remember. And then we're going to use 9.8 meters per second as G because we're on Earth. Okay, so the first thing I like to do is I like to write what I know. So I know that my mass is 65 kilograms. I know that G is 9.8 meters per second squared. And I know that, or I don't know Fg, but I do know the units for that are going to be newtons. Okay, and so my formula is Fg is equal to mass times gravity. Okay, now if we say they gave us the F and we wanted, let's just say they gave us F and they gave us G and we wanted M. You could put this in the triangle if you wanted to, okay, and it would look like this. The triangle is kind of lopsided. I'm going to put my M, sorry, I almost did it wrong. I'm going to put my M here and my G here because those two get multiplied. And then I'm going to put my F here. Here we're just looking for force, so we don't really need the triangle, but just in case they give you a different type of problem. Okay, so I'm going to have 65 times 9.8, and I'm going to get 637 newtons, and that's going to be my answer. Okay. So these problems aren't too bad, and which is good because like for next week, for example, solving for FG or your weight is going to be just like a teeny part of the larger problem, or the larger thing that we're trying to solve. So it's kind of nice that this is relatively easy. So now we can talk about apparent weight. Okay, this is a little different. So apparent weight is the force you experience as a result of all the forces acting on it, giving you acceleration. So for example, you can see in this picture that this kid is on one of those like Tower of Terror or something like that kind of rides, and I guess he didn't put on his seatbelt or whatever, and so this person is like in the air, right? This person does not weigh zero. It's just at this point they had apparent weightlessness. Okay, they appeared to be weightless, but they weren't actually weightless, and it had to do with the acceleration of that ride and gravity interacting together. Okay. A lot of times when I was in the face-to-face class, we would do a lab where we had kids. We had an elevator at our school because it was 3 floors, and we would send kids into the elevator with a scale, and we would have them actually record their weight on the scale, accelerating upwards, accelerating downwards, and at rest, and they would actually see that their weight was different based on how they were moving in the elevator. So here is an example of one of those elevator problems, just to give you an idea of how your weight can change in the elevator. So I'm going to do pink for at rest, and then I'll change my color for while I'm accelerating, so then you get these two, so you'll see the two different equations. So this is our mass, and this is going to be our mass regardless. Okay, now we're starting from rest. Okay, and the elevator is going to accelerate upward at 2 meters per second. So that's going to be our A. And then our time is 2 seconds, and then it's going to continue at a constant speed. Now it says, is the scale reading during acceleration greater than, equal to, or less than the scale reading when the elevator is at rest? So let's write all the things that we know. This is always the first thing that I do, because honestly, I don't like going back and looking at these long paragraphs. So I just write everything that they give me here. And some of that information I may not need it, like starting from rest. But I'm going to go ahead and write it down anyway, and that way I don't have to go back and look at that that paragraph of information anymore. I can just kind of stick with what I've got over here on the left. Okay, so at rest, I'm just going to use this regular FG equals mg, and I'm going to solve for FG. And so I'm going to have 75 times 9.8. Okay, so that's my weight at rest. Now let's do I'm going to do blue for the accelerating. Okay, so while I'm accelerating, so we're going to accelerate upward. Okay, so we're going to use the same FG formula, except our acceleration in the upward direction is going to kind of counteract our acceleration in the downward direction, if that makes sense, or our gravity. Okay, so what I'm going to do is I'm going to solve for my new G. Okay, so I'm going to call this new G, and it's going to be equal to 9.8 minus that 2. Okay, so that's going to be 7.8. Okay, so that's what I'm going to put in the equation while I'm accelerating. Now, if you've, if you have a good handle on math, you might realize that 75 times 9.8 is going to be more than 75 times 7.8. But, if you don't notice that right away, that's okay. I've done this problem a few times, so, I notice these things, but, if you don't right away or you just want to check, go ahead and do the math, right? You don't get bonus points for solving the problems, in your head or anything like that. Okay, so while we're moving up, our acceleration or our weight is 585 newtons. Okay, so it's going to be less while we're accelerating. Okay, so when they said, is it greater than, equal to, or less, we can circle less. Okay, and that just kind of shows you, you could, if you wanted to on your own, you could do an accelerating downwards one. And instead of having this be positive 2, you could have it be negative 2. And then you could, you could add basically 2 to this 9.8 and see what would happen. And since you're going to have a larger acceleration, you'll have a larger weight. But, you can do that one for yourself if you want, just to see how it feels and just to kind of practice with it. So here's our normal force. And the normal force has to do with when you're in contact with something. Okay, so it's a perpendicular contact force exerted by a surface on another object. So you'll remember when we did our free body diagrams, for example, right, if we're touching something, let's say that's touching the ground, we would have our FG going this way, our weight, right? And then we would have our normal force going this way, and they would be equal to each other. Okay. And so you're only going to have this when you're touching another object. You're not going to have this when you're in free fall or anything like that, or because it's only has to do when you're touching with things. And it basically keeps the object from falling through. If the gravity was more than the normal force, the object would kind of fall through the surface or fall through the table, which I know feels weird because it doesn't happen. Or if the normal force was more than the gravitational force, then the object might rise into the air, which again, that doesn't happen. So it just feels silly to us, but that's why. Okay, and let me also do this. Your normal force is equal to your weight. So if you solve for FG, that's also your normal force. So if they ask you to solve for the normal force, that's basically like telling you to solve for FG or for your weight. So keep that in mind when you're solving for normal force. Now friction. Friction has a couple different ways. There's kinetic friction and static friction. We'll talk about the difference between the two. But both of them basically have something called a coefficient of friction. Okay, let me see if I can. I'm not sure that yellow will show up. Here's green. This right here, oh, it's still yellow. Well, now it's showing up. That is our coefficient of friction. Okay, and it's based on the surface. So for example, a carpeted surface is going to have a higher coefficient of friction than, say, ice, because ice is really smooth and things, push across the ice very easily. There's not a lot of friction on ice, but there is a lot of friction on carpet. So that coefficient of friction depends on the surface. Okay, and then your Fn, that's your normal force, and that's just your weight. Okay. So you may see it in the course, you may see something like this. They might write it that way, and that's just, that's fine. It's the same thing. That's their friction. This is their coefficient of friction, and this is the weight. I did see somewhere in the course where instead of this weird U, they wrote M, which I don't know if that's a typo or they were just, that's another way to write the U. I've never seen it written that way, so I'm thinking it's a typo, but it doesn't really mean your mass, okay, because that doesn't make sense. And then if you have an angled problem, like you're have to deal with friction on an angled surface, you would use this formula. So you would use the y component of your friction plus the n, which is your normal force, minus Fg. Okay, so you could also write this formula this way. And because the surface is angled, your normal isn't actually going to be equal to your gravity because your normal is always perpendicular and your gravity is always down. So that's why they have these two like this. It's not like, otherwise it would make no sense, right? If they're equal to each other, why even bother putting them in a problem? Okay, so you could write the formula like this if you wanted to. Okay. Now, so let's talk more about friction. So friction is always opposite the motion, okay, which is handy. For example, if you want to park on a hill, your car, you'll need some friction between the tires and the road in order to get it to stay there. In order to stay sitting in a seat, for example, to work on your virtual school homework or your regular school homework, you've got to have friction between your bum and the leg and your legs and the chair. Otherwise, you would just slip and slide and you wouldn't be able to sit still. Okay. Sometimes I think my son doesn't have any friction between himself and the chair because he just like slips and slides everywhere, but that's just because he's busy. Um, so friction is always opposite the motion, and it's actually pretty handy, right? Because if we didn't have friction, a lot of the things that we like to do, for example, like walking, we would not be able to do, right? If there wasn't friction on the ground, we wouldn't be able to walk. We would just slip and slide everywhere, and that would be kind of annoying. So static friction is the friction of not moving, and kinetic friction is the friction of moving. So, for example, if you're trying to push something across the floor, like in your friction lab, before that thing starts moving, and when you're pushing on it and it's not moving, that's the static friction. And then once it starts moving, that's the kinetic friction. So to calculate kinetic friction, again, we have this coefficient of kinetic friction, which is this little u, and then we have our normal force, which is basically your weight. Okay, so let's try this problem. Okay, so let's see what we've got here. We have a girl exerting a 36 Newton force. So this is going to be her applied force. And she's pulling a 52 Newton sled. So this is the FG of the sled across a cement sidewalk at a constant speed. What is the coefficient of kinetic friction? That's that U, that weird looking U, between the sidewalk and the metal sled runners, and we're going to ignore air resistance. So what do we know? We know our applied force is 36 newtons. We know our weight is 52 newtons, which is also the normal force, which I'm going to go ahead and write this here so I don't forget. And then I want to know the kinetic friction, or the coefficient of friction. The coefficient of friction does not have a unit, which is handy because then you can't get points marked off for not putting the unit, right? So now let's draw a picture of what's going on here, or let's draw our free body diagram. Okay, so here's our sled. We've got our applied force in this direction. We have our kinetic friction in this direction. I'm just going to call it FF though. We have a normal force in the y direction. and we have a weight or a gravity force in the y direction. So like I did last week, I'm going to go ahead and I'm just going to kind of make some notes here to myself. For example, my normal force is equal to my gravitational force. I want to put that there. And then my friction force is going to be less than my applied force. If my friction force was more than my applied force, then my object wouldn't move. It would stay still. Okay, so let's see what we've got here. So let's go ahead and let's solve this. Okay, so what I need to do is I'm going to take my friction formula and I'm going to have U and Fn. Okay, now I need to solve for U. So I'm going to do U Fn and then F friction, and I'm solving for U. So my U is going to be equal to my force of friction over my normal force. Sorry. So I realized I made a mistake here. Do you see how this says constant speed up here? Since we're moving at a constant speed, our friction is going to be equal to our applied force. Sorry, we're not accelerating, so our applied force is not more. I was just looking at this here and I was like, it doesn't look right. Okay, so our applied force is going to be equal to our friction force. Otherwise, we wouldn't be able to solve this problem. Well, we could, but they would have had to give us more information. So I'm going to take my 36 and I'm going to divide by 52 because that's my normal force. And I'm going to get 0.69 as my U. Okay, now if I'm looking and I'm solving these problems and I'm trying to see if my answer makes sense, okay, your coefficient of friction is always going to be less than 1. So since this is 0.69, that's good. That's, less than 1. And we're closer to 1 than we are to 0, right? So this would be a relatively high coefficient of friction. But then I look and I see that we're pulling it across a cement sidewalk, and cement is very, very rough, right? If you've ever fallen on cement, you know. Cement's very, very rough. And so having a coefficient of friction on the higher end of things makes sense since we're on that rough surface. Okay, so that this answer makes sense to me. So I like to just kind of like make sure my answer makes sense. Like I've seen students, and I've done it before on accident, I've done like 52 over 36, and then I'll get a number that's greater than 1, and I'll go, that doesn't make sense. Coefficient of frictions are supposed to be less than 1. And so I'll see that, I'll realize that I put my numbers upside down and I can go back and fix them. So, just kind of keep that in mind. Now let's talk about static friction. Static friction is the same thing, the same type of formula. The only difference is they put this, in order to have the formula like really to be super accurate, you'd want to put this right here, and that's because your coefficient of static friction has to be less than or equal to those, because once it is more than, it will start moving. Okay, so if it's less than or equal to, that means it's still going to be still. Okay, so that's why they have that, they have this guy in here. Now on their class website, I think they just have an equal sign, and that's fine. It doesn't really change anything. So now let's try and do a coefficient of friction formula. And I'm just playing around with colors today. That's why I'm using all these different colors, kind of testing out the darker background. So that's just why there's always so many colors. So we need to move 105 kilogram sofa. That's going to be the mass of our sofa, to a different location in the room. It takes a force of 102 newtons to get it moving. Okay, so this is going to be our applied force. What is the coefficient of static friction between the sofa and the carpet? Okay, so I'm going to write what I know here. My mass is 105 kilograms. My applied force is 102. And since that's the exact force I need to get it moving, our applied force is actually going to equal our friction force. So I'm going to put that there so I don't forget like I did last time. And then I'm going to put my gravity here, even though I've got it memorized, but I'm going to go ahead and put it there anyway. And then I'm going to put, sorry, this here. So I remember that that's what I'm looking for. Okay, so the first thing I want to do is I want to draw a free body diagram for what's going on in here. Okay, just because it gives me a visual picture of, you know, what I'm seeing or what's happening, and it helps me make sure I don't forget a force, which in these simple problems, it's not such a big deal, but when we get to more difficult ones, it will be important. So I have my normal force going up. I have my gravity force going down. I have my applied force here, and I have my friction force here. Okay, and then I'm just going to do this again, just so I don't forget. My normal force is equal to my gravity force, and I'm also going to write that my friction is equal to my applied force. Can you see that I'm like paranoid of forgetting that again? And then I'm going to look at my formula. Okay, so my formula is friction is less than or equal to the coefficient of friction plus the normal force, right? And so the first thing I notice is that I don't know the normal force yet, right? They gave me the mass, but they didn't give me the normal force. So I'm going to have to figure that out. So I'm going to go over here, and I'm going to figure out my normal force first, right? Which is just equal to mass times gravity because it's equivalent to our weight. So I'm going to put 105 times 9.8. And I'm going to get 1029 newtons. Now that I have that, I can go ahead and I can start moving again. I hope this is the same color that I chose before. Okay, so now I have, now I want this U, so I'm going to go ahead and I'm going to put this in a triangle. Okay, so I have my U, Fn, force of friction, solving for U. So I have U equals force of friction over my normal force. My force of friction is 102. And then my, sorry, it should be 1029. You can see how these ends cancel out. That's why U is actually a dimensionless unit. And I'm going to get 0.1. Okay, that is a small force of friction. It seems odd to me that it would be so small for the carpet, but you know, our applied force was not huge, so that's why it was so small. But anyway, it's less than 1, so that at least lets me know that I did it right. So that's how you would solve a static friction problem. It's exactly the same as a kinetic friction problem. It's just static friction. That's really the only difference. Okay, so now let's try an angled friction problem. These are a little more difficult, and I wanted to try one because why not? I'd rather you see it here than on a test or something like that. Okay, so we have a mass of 20 kilograms. We have an applied force of 150 newtons, and our theta is 25 degrees above the horizontal. And then it also tells me my coefficient of friction. Okay, and then it says what is the force of friction. Okay, so we're looking for FF. Okay, so I'm going to write what I know over here. Theta is 25 degrees. My coefficient of friction is 0.150. And my force of friction, I don't know what that is, but I do know the units are going to be newtons. Okay, so the first thing I want to do is I want to kind of draw a free body diagram of what's going on here. Okay, so that's my first step. Okay, and I'm going to put it in a different color just so we can kind of keep track. So here's my block. It's going to have a normal force. Um, Now we're not actually on an angled surface, it's being pulled at an angle. Okay, so you can think of this as like, if you're dragging a wagon, right, a lot of times you don't keep the handle of the wagon completely horizontal to the floor. You've got it angled a little bit, to reach your hands. And so that's kind of what's going on here. Okay, so our applied force is like this. But our friction force is still going to be horizontal along the floor. Okay, so then we can take this picture and we can kind of break it into like a coordinate plane or whatever, whatever they call this when you're doing math. Okay, and so then I'm going to break it into the two parts. Okay, so my x-axis, this is my applied force in the x direction. And then I'm going to have an applied force in the y direction as well, right? Because we know how to resolve vectors. That's old news now. Okay, and since our friction is in the x direction, we really only care about the friction or the applied force in the x direction as well. Okay, that's all we really care about. Okay, so now what I'm going to do is I'm going to go ahead and I'm going to try and work through my problem. Okay, so step 2 is I'm going to go ahead and work through my problem. So remember, for angled problems, we're going to have FG plus Fn minus, oh, sorry, this is FG. I mean F, Fy, sorry. Okay, and so I think I said that we weren't going to deal with the F. G, but we're actually going to have our Fy here, and the reason we're using Fy here is because our normal force is in the y direction. Our gravity force is in the y direction, or our weight. So we're going to use this all in the same direction. Okay. So here we go. We're going to solve for our Fn. So I'm going to take this guy and I'm going to move him over here. And I'm going to take this guy and move him over here too, right? Because I need my normal, I need to know what my normal force is in order to do my friction formula, right? Because that's what my friction formula has in it. This is a minus, sorry, so this should be a plus. I like made that little mark and I was like, oh, look, it's exactly what I wanted, but it wasn't actually exactly what I wanted. Okay, so then I'm going to do my Fg is mass times gravity, right? So my mass is 20, my gravity is 9.8. And I'm going to take away from that the y component of my velocity now, or my friction, my applied force. Now, remember, how do we calculate a y component, right? Let's think about that. We calculate a y component using that formula, A sine theta. So that's exactly what I'm going to do right here. Okay, I'm going to put 150 sine 25. Okay, that's how I'm gonna solve that. Okay, so then I'm gonna have 196 minus 63.39, which is going to give me 132.61 newtons for my normal force. And now, finally, that I have my normal force, I can actually go ahead and I can solve for my force of friction, which is what they asked me for in the first place. So you can see that sometimes these questions get a little involved. But I'd rather, do the work, even if it is involved, than, try and do it in my head and not get the right answer. Because you get points for the right answer. You don't get points for doing it all in your head and getting the wrong answer. And you get points for showing your work, so you might as well anyway. I mean, and so our force of friction is 19.89 newtons. Okay, so that's like an angled friction problem. So hopefully that helps. And we just have to break it into components, just like we did last unit. Okay, so now let's do a tension problem. Okay, so our tension is always going to be our F is equal to our tension minus our gravity, and this is for like things that are hanging. For example, so we assume that the strings and the ropes have no mass, and we assume the tension is the weight of everything hanging from it. So if you have like 6 buckets, it would be the weight of all 6 buckets, not just the one. Okay, so now we can try a tension problem. Okay, so let's write what we know. Let's see what they tell us. They tell us that we have a 50 kilogram bucket. So that's our mass. They say the rope will not break, the rope will not break if the tension is 525 or less. Okay. So this is kind of what we want our tension force to be. And it says the bucket started at rest. So that's our V0. And after being lifted 3 meters, this would be our distance. It's moving at 3 meters per second. And then it says if the acceleration is constant, is the rope in danger of breaking? So let's write all the things that we know. We know that our mass is 50 kilograms. We know that we want our tension to be less than or equal to 525. We know our V0 is 0. We know D is 3 meters. We know our VF is 3 meters per second. And then we don't know our acceleration. Okay, so the first thing we need to do is, again, I'm going to draw a free body diagram. Okay, I'm going to go ahead and keep it in yellow. We're not going to have a normal force here because we're not sitting on something. Oops, sorry, I just totally drew that wrong. I'm actually embarrassed I even put it an arrow facing the object. That's a huge no-no. And then our gravity. Okay. So, and then our acceleration is in this direction. And our gravity is in this direction. Okay, so that's our free body diagram. So then the next thing we need to do is we need to solve for acceleration because we can't do anything without that. Okay, so I'm going to try and get that. Okay, so I'm going to use this formula. Okay, I'm going to use this formula. And I chose this one because I have an initial and a final velocity, and I have a height or a distance, and I don't have an acceleration. So that's why I chose this one. So I know some of you guys were like, how do you know which formula to choose? You have to choose a formula that you know, has what you have and doesn't have what you need. And you just have to, you know, the more you do these problems, the easier it'll get. Okay, so I just took 3 times 3, which is 9, and I did 2 times 3, which is 6, to get 6a. And I'm just going to divide this, and so I'm going to get like 1.5 meters per second squared equals a. Okay, I feel like 9 divided by 6. Yeah, it's 1.5. Okay, just to make sure. And then I'm going to actually, you know, start solving for tension. Okay, so tension is equal to, I'm gonna do it right here. We have F net is equal to our tension force minus our gravity force. Okay, and we are looking for the tension force. Okay, so I'm going to take this gravity force and I'm going to move it over here. Okay, so then I have F tension is equal to F net plus FG. Okay, so now let's think about this. Our F net is equal to mass times acceleration, and our gravity force is mass times gravity. Okay, so that's what we're going to put in here. So I'm going to put 50 times 1.5, and then I'm going to do 50 times 9.8. Okay, and I'm going to get 75 plus 490. And if I was a math teacher, they'd get super mad. You're not supposed to draw arrows like this. You're supposed to start with enough space. And so 75 plus 490 is going to be 565. So our rope is going to break. Okay, that bucket is too heavy. Okay, because that's more than 525. So that's how we can do a tension problem. Okay, and then the last things I really wanted to discuss today are springs. Okay, and so usually I put this in a different section, but this is how our class is structured. So Hooke's law is, it is a type of force. It's a spring force, and the force exerted by a spring is equal to the spring constant times the distance the spring is compressed or stretched from equilibrium. So this right here, this is a spring constant, and this negative is part of the equation. So you have to keep that negative in the equation. It's F equals negative kx. It is not F equals kx. That negative has to be there. Okay. And then your x is your distance. Okay. So your spring constant depends on the stiffness of the spring. So for example, a slinky is going to have a different spring constant than, say, the spring on like one of those big trampolines that kids use. So it's completely different for each spring. They're all going to have a different spring constant. And so we can actually solve for a spring constant formula. Okay, so let's see what we've got. So we've got 18 centimeters. This is our x. And our potatoes weigh 56 newtons, and it's just suspended from the end. And so we want to determine the spring constant. So our x is equal to 18 centimeters. Our force is 56 newtons. And we want that spring constant. Okay. And so this is in centimeters, so we have to convert that to meters because, we need everything to be in the same units. And so, yeah, it has to be in meters. So we'll do, there's 100 centimeters in 1 meter. So we're going to get 0.18 meters, and that makes sense, right? Because it's 18 centimeters is smaller than a meter, so we would get a small number. That makes sense. And then we're just going to solve. Okay. So, that was weird. I'm going to have negative k equals f over x. And then I'm basically going to multiply each side by -1. So I'm going to get k equals negative f over x. Okay. So then I'm going to have 56 over 0.18. And I'm going to get negative 311.1. That's our spring constant. Okay, so that's how you do that type of problem. So they're not super hard. So, they added springs in here, but, it's not going to make or break us. It's not super difficult. Now, the second half of this unit is a little more difficult. So I encourage you to save some time for that because you'll need it. It's the problems are more involved, and so it'll be important, that you know how to do that, those problems, and you want to spend that time on them. So anyway, that's at least types of forces. And then next week we'll kind of review for that application of Newton's laws test, and we'll do some of those more involved problems, like in the system and slope section. Particularly, I think is the problems are just kind of long. So